So today we are very happy to have Svetlana Makarova from the Australian National University, who will talk about contractions via moduli of sheaves.
All right. First of all, thanks to the organizers and especially to JS for inviting me to talk at the seminar. So full disclosure, I am an algebraic geometry, as you may have gathered from my title and abstract. But the point of the talk is probably to illustrate how categorical methods can be useful for doing explicit geometric constructions, like specifically contractions. So I will talk about moduli problems, and to everyone in the room, moduli problems should be very easy because they are essentially contravariant functors. Then I will briefly define stacks, and again, I believe that the audience may have better familiarity with stacks than I do, at least in the categorical setting. And then I will return to talking about geometry. I will define what good moduli spaces are, and I will give some examples. So I will show our main theorem and show that in many applications, our theorem gives some nice explicit geometric constructions. And this work is joined with Andres Fernandez Herrero, who is based at University of Pennsylvania. But we did it during his visit last year, like when he came to ANU. And you can see his picture on the slides. Okay, so first of all, I will talk about I want to fix like the main geometric questions, the main geometric question that drives the project. So if X is a smooth projective variety over a field, and in this case, the field is arbitrary, doesn't have to be algebraically closed, doesn't have to be characteristic zero. If we have a closed subvariety, so we have Y inside of X, and let's say that we have a surjective morphism from Y to B. For example, it could be a P1 fibration or just contracting Y to a point. So this is a perfectly valid surjective morphism. The question is when we can replace Y inside of X with B inside of X. So when does there exist a space or a scheme X bar that has a closed subvariety B, a surjection from X, and such that on the complement, these two are isomorphic. So X minus Y is isomorphic to X bar minus B. So these are open complements. And in algebraic geometry, the main construction that gives us pictures like this is that of a blow-up. So if we have, for example, P2, we can pick a point, and this point can be replaced with, so like when we remove the point in P2, we can think of the geometry around this point. So like we replace the geometry of the point with the geometry of lines passing through the point. So with this gives us a way of gluing P1 instead of a point inside of some variety X that is called the blow-up of P2 in a point. Sorry, P2. And then P2 will be our X bar in this picture. And we address this problem by looking at by replacing X with a certain moduli problem, and like since there are category theorists in the room, the moduli problem, as you expect, will be the representable functor, or like when we pass to stacks, it will be like a slight, like a fancier version of a representable functor, which is a little bit underwhelming on the one hand, but on the other hand, it's still pretty exciting that simple objects like representable functors can give us some interesting results. So what is a moduli functor? So when we want to classify any type of objects, groups, algebras, varieties, in our case, we will be classifying sheaves on varieties, specifically ideal sheaves mostly. We can also talk about like I've also worked on like moduli of representations or moduli of objects in abelian categories. So when we want to tell how they glue into one object, a natural way is to consider families. So if we have a base scheme B, if we want to say that two objects differ slightly, we say that okay, if we consider family over B, if we can vary the object along the points of B somehow, like in a smooth or flat, like in algebraic geometry, usually we say flat way. So if we can vary it in a reasonable way, then we can also say that these objects are close to each other, air quotes, if they are close in the topology on B. And if we have a morphism between the base schemes, F, from B prime to B, then we can consider the pullback of families by pictorially for each point of B prime, we associate the object from the image of this point. And I have already foreshadowed this. What you see, like families and pullbacks of families, this defines a contravariant functor from schemes to sets, such that over a point, spec K is a point, we get the set of isomorphism classes of objects that we want to classify. So for example, we can talk about classifying, like the simplest example would be classifying vector spaces. Then M of spec K, we could say that these are vector spaces of a fixed dimension, vector spaces of dimension n. Then M on a base scheme B, like a reasonable up to isomorphism. So this, we know there is only one space like this. Then the moduli functor at B would be the set of isomorphism classes of vector bundles on B. On B of the fixed rank n. And we know that not all functors are created equal. Some of them are representable. And in this case, the representing object is called the fine moduli space. So, and then via this isomorphism of the functor M, with the representable functor. We can choose the universal family. We can denote it by E in M of M. It is something that corresponds to the identity morphism. So like the Yonah deconstruction essentially gives us the existence of the universal family. All right. Example number 1, functor of points, which is in this room, it should be called the representable functor. So if X is a smooth projective variety over a field K, then we can define M of on a test scheme T as home from T to X, and then X is trivially the fine moduli space for M, because fine moduli space is the algebraic geometry word for representing object. And if K is a field, if capital K is a field extension of the base field, then M at spec K will give us the K points of our variety X. So like if like for people doing arithmetic, which probably not a lot of people that do arithmetic here, but we can talk about a variety over a field FP, and then X of FP to the N will tell us all points that are defined over the extension of that field. So there, like you would expect to see more points. But because we do algebraic geometry, we can also talk not about the functor of points, but we can talk about functor of several points, which in algebraic geometry is also known as the Hilbert scheme of points, or I guess I should say Hilbert functor. And then it is a theorem of Grothendieck that the Hilbert functor is representable by a scheme which is called the Hilbert scheme. So if we take a smooth projective variety over a field K and a natural number, then on a test scheme T, we define the set of families. It will be, these will be schemes Z from subschemes of X cross T. So if we think of the functor of points, so if we compare with the case L equal to 1, we have M of T is home from T to X. But what are morphisms from T to X? So if we go back to our first year and think what functions are defined as graphs in X cross T, such that the projection from Z to T is an isomorphism. And now, in this case, the functor of several points will be classifying multi-valued functions. So for each point of T, we can pick several points of X, and sometimes these points may collide, which is why we don't say that Z is a subscheme of L points, but instead we say that Z is a length L subscheme. So this is where the difference between So for example, spec of k epsilon mod epsilon squared is a length 2 scheme, which geometrically has 1 point, but we count it with multiplicity 2. All right. Any questions up to now? Okay, so we have seen two examples where the moduli functor is representable, but in general, they are very rarely representable. And historically, like chronologically, there have been two solutions. And the first was to throw out the non-schematic locus by means of introducing some stability and doing GIT. Stability, semi-stability, GIT. And the second solution, like the more modern solution, is to expand the notion of a moduli functor by saying that, okay, we now allow more geometric objects. And so we want to do geometry with more general objects than just schemes or even algebraic spaces. And thus, we are now studying stacks. So when we say that, if we ask the moduli functor to remember automorphisms, so we allow the values not in sets but in groupoids. That is where stacks appear. And the advantages are that this machinery still works when GIT cannot be applied. So if we don't know enough about the structure of our moduli problem, so like for representations of quivers, for example, we know that they can be overparameterized by a huge set of matrices. But for objects in an abelian category, like we don't know how to parameterize them. But still, we can define the notion of a moduli functor, like of objects in an abelian category. And the second advantage is that that this approach is coordinate free. So when we choose an overparameterization of the moduli problem, it is essentially choosing coordinates. Then we need to choose stability, which gives us more coordinates. And it is like, for me, it's hard to keep track of coordinates and changes of coordinates. And this makes the structure of the moduli problem, like the intrinsic approach makes the structure of the moduli problem more clear. And this helped us get like a new explicit result for moduli of quiver representations, where we just ran the fancy machinery, and then we got like a very explicit result about the global generation of determinantal line bundles. Okay, so as I said, when we talk about stacks, we replace the category of sets with the category of groupoids, or rather the two category. And then we define like a contravariant pseudo-functor to groupoids is called a pre-stack. And if we impose in addition a gluing condition, then we get a stack. A gluing condition with respect to some choice of topology. For stacks, like the easiest choice of topology is the Ital topology. People also work with FPPF topology, but both topologies give the same notion of algebraic stack. So we say that a stack is algebraic if there is a smooth surjection from some scheme U, and such that the diagonal is representable. And representability of the diagonal means that, so a morphism of stacks is representable if for all maps from an algebraic space T to Y, the pullback is an algebraic space. And algebraic spaces are now sufficiently close to schemes that we can talk about smoothness of morphisms between them. And so representability of the diagonal in particular allows us to say that if we have any morphism from a scheme to M, then this morphism is representable. And then we can talk about smoothness, then we can talk about what it means to be a smooth morphism. Okay, and we call these stacks satisfying this condition algebraic, or also Artin stacks, although the main idea is that they are more geometric, so we can do geometry with them. So in that sense, the name is a bit of a misnomer. And the trivial example is categorically we can take, so if we take the M of just spec K, and now let's say that K is algebraically closed of characteristic 0 for simplicity, then the groupoid at the point is equivalent to the category with one object and GM automorphisms of this object. So GM of spec K is equal to the automorphisms of this unique object star. Okay, so in that sense, when we have one object and some automorphisms of the object, this is probably the simplest example of a groupoid that is not a set, or not a setoid. And geometrically, it is BGM, the classifying stack of GM. And on a scheme T, it is defined as GM torsors over T. So we have P to T such that GM acts on P compatibly with the projection, and each fiber is a GM torsor, or FPPF locally, we can say that this P should be isomorphic to T cross GM locally in our topology. And morphisms in M of T, in the groupoid M of T, are isomorphisms, as you would expect, because we can't add anything else, like we can't add anything non-invertible.
Sorry, Sveta. Can you say again what GM is?
Oh, sorry. Let me clarify that GM is the multiplicative group of our field.
Okay, thank you.
So these are scalars minus 0. Thank you. Any other questions? Okay. Example 1. This is where I will give a fancier presentation of our representable functor. So if X is a smooth projective variety over a field K, then we can define M of T as the groupoid of ideal sheaves of length 1 subschemes. And if K is algebraically closed, then we can replace this with just saying such that Z is a closed point. But when K is not algebraically closed, the problem is that there are points that are defined over finite field extensions, and then we have closed points that have bigger lengths because the field extension has a positive dimension over our base field. And morphisms, as you expect, are isomorphisms of sheaves. And let me copy this example on the right. I will actually denote this example H of T. It will be ideal sheaf of a length 1 subscheme. Okay, because as I said, this will be the main example of the talk. And because X is smooth, hence normal, in dimension bigger than 2, M will actually be isomorphic to X cross BGM. So we didn't go very far from our representable functors. And why is that? So smooth dimension at least 2 implies that if ideal sheaves of 2 points are isomorphic, then the points are equal. And this is, like, I want to note that this is here, it is not an equality of submodules of the structure sheaf. It is really an isomorphism of abstract sheaves. So this follows from the Hartog's lemma because for 2 sheaves, like the point, the ideal sheaf of point gives us the functions that vanish at this particular point. So by Hartog's lemma, if we have 2 functions that agree on away from a codimension 2 locus, then the 2 functions must actually coincide. So they must define the, so they must vanish at the same point. And in a similar way, we can get a stacky version of the second example, where we have ideal sheaves of several points. So now we take ideal sheaves of a T-flat subscheme as before, such that the restriction is the length L subscheme again as before. But in this case, we don't just take isomorphism classes, we actually take the whole groupoid of objects plus automorphisms. And the funny example that basically was the starting point of the paper. So let me now assume that we have a rigid, smooth rational curve, or essentially, like over an algebraically closed field, it is just a P1. So we have P1 embedded into X, such that the normal bundle splits into line bundles of non-positive degree. So there is a non-positivity condition. And the points of U of the points of the stack U. And let me now just talk about the values at spec K, or maybe some field extension. The points will be of two types. First, we have the familiar points, the familiar picture of ideal sheaves. Sheaves of ideal sheaves of points of length 1 subschemes. But we also add F, sheaves F, such that there exists a short exact sequence of this form. So these are non-pure sheaves. They will have torsion. There will be a part supported, there will be a component supported on P1 that is included into F. And the quotient is the ideal sheaf of P1. And let me see pictorially what this means. If I have so this will be my red part. So let me look at a symmetrically looking locus of ideal sheaves of points. So these will be ideal sheaves of points such that X is in our chosen P1. What happens then? All functions that vanish on P1 will vanish at the point on P1. So we have an embedding of sheaves, an inclusion of sheaves, the ideal sheaf of P1 into the ideal sheaf of the point. And the quotient of the embedding is, so like if we take all functions on the variety that vanish at a point, and we quotient it out by all functions on the variety that vanish at P1, what remains is functions on P1 that vanish at the point. So this is precisely P1 minus 1. Functions on P1 that vanish at a point. And the reason why I don't write the ideal sheaf of X in P1 is because all sheaves of degree -1 on P1 are isomorphic. So I can write this. And moreover, for the future, I want to separate two cases. So the sheaf F, the non-pure sheaf F, can be non-split if the sequence does not split, and it can be just the direct sum of all P1 minus 1 plus the ideal sheaf of P1. So this is the case when the short exact sequence splits. Okay, and the stack X, the stack U is defined as a substack of the stack of coherent sheaves on X. With trivial determinant. And since it is a substack, it is a subfunctor. So on each T, is the set of sheaves F such that for each fiber of T, this sheaf lives in our picture. It is of the two described types. Okay, any questions about this definition? Okay, if there are no questions, I will move on to, oops, oh no. Okay, all right. Sorry, I'll come back to it. I will define good moduli spaces because now, like the original goal was to talk about explicit geometric constructions, and they usually live in the category of schemes. So considering good moduli spaces is a way of going from stacks to the category of algebraic spaces, which is as close to schemes as we can get via these constructions. So a good moduli space for M is, so you can read the definition, which doesn't make a lot of sense. So it is a morphism from M to an algebraic space such that the push-forward functor on quasi-coherent sheaves is exact, and it takes the structure sheaf to the structure sheaf. But the main idea, like maybe the main consequence that you want to remember is that this the main consequence is that this functor phi is this morphism phi is the initial morphism from M to algebraic spaces. Among morphisms M to T, where T is an algebraic space. So this is the closest approximation of the stack that satisfies extra nice properties that also give a lot of geometric corollaries. So the main geometric example is if G is a group that acts on a variety X, and if it admits a good quotient in the sense of geometric invariant theory, then we can consider the quotient stack X mod G, or no? And the good quotient will be the good moduli space, and hence the terminology that Jared chose, Jared Alpar. So a particular example would be GM acting on a point. The only quotient that you can come up with is the point, and it is the good quotient. So BGM to the point is a good moduli space. Good moduli spaces actually, so one can actually determine when a good moduli space exists. So if M is a nice stack, and the stack co-x, even with, like, we can also fix the determinant. And our stack is, we verify that our stack U is an open substack here. So it is also of this nice type. Then Alper, Halpern, Leisner, and Heinloth proved that it has a separated good moduli space if and only if M is locally linearly reductive, which means that every point has a closed point in the closure, which does not always exist even for algebraic spaces. So this is a non-trivial condition. And every closed point has a linearly reductive stabilizer. And moreover, the stack is theta reductive and S complete. So these are, for algebraic geometers, they call them valuative criteria for stacks. For category theorists, I would say that these are right-lifting properties with respect to some maps. So this is something that can be explicitly verified for a particular stack. And moreover, M is proper if and only if the stack satisfies the existence of the valuative criterion properness, which is again a right-lifting property. So this is a right-lifting property, and these are unique right-lifting properties with respect to some sets of maps. And as I said before, BGM to a point is a good moduli space. Now, the stack of ideal sheaves of one point admits the good moduli space X. So I denoted it by H. So this is a good moduli space by our description as a product and by example 0. And example 2, ideal sheaves of L points also admit a good moduli space by the similar reasoning as before, because BGM admits a good moduli space, and X is already a scheme, or Hilb L of X is already a scheme, so it is its own good moduli space. Maybe I could write it here, example 0 prime. If X is a scheme, then X to X is a good moduli space. Like whatever conditions we imposed in the definition, they are satisfied for the identity morphism. So our example 3, the stack U has a good moduli space. And we actually prove it in bigger generality. So we say that this stack does not just have to depend on, so it can depend on alpha and L. And in this example that I showed you before, so here, this example could actually be called U P1, 1. So we can replace 1 with any number of points. We can replace P1 with some families of subschemes that satisfy technical conditions that enable us to prove the existence of good moduli spaces. And this stack has a good moduli space, which is denoted. So we denoted Hilb L X alpha. Sorry, I think in this case, I should write Hilb 1 X alpha. All right, and before I drew a symmetric picture, and it was on purpose, because now we can say that instead of taking just this part, so this is H. We can now take the other part here, and we call it U circle. And we verify again that this has a good moduli space. And there are, I actually have a different picture here. So there are some properties of good moduli spaces that help us understand what's going on and why we have this picture that I call a beyond GIT wall crossing. So because we call it wall crossing, I drew a wall here, so you know that we are crossing a wall. So there are some properties of good moduli spaces that we would like to use. Again, theorem by Alper. Let's say that M to M is a good moduli space. Then we have a lot of corollaries. So this map phi is universally submersive, in particular surjective. Then closed points of M have a unique closed point in the pre-image. So closed points of the good moduli space correspond to closed points of M. Closed points of the stack. And I already said that phi is universal. So in particular, on this slide, we see that U alpha L0 has a map to an algebraic space here, and we have a map to another stack, which admits a map to a different algebraic space. And so by universality, we have that this map P2 exists. And in a similar way here, so the stack H has a map to this stack and to this algebraic space. And it is also embedded as an open substack into U alpha L. And so because we have this composition, again, by universality, we get a morphism to another good moduli space. So this picture induces so the example where we have a rigid P1 with non-positive normal bundles. In this picture, we have U alpha 1 admits a good moduli space, which by example I said is X. Sorry, this was H. H is an open substack in U. U admits a good moduli space, which I will denote X bar. So it is Hilb 1X P1. So we get a map like this. And now I want to return to the property about closed points of the good moduli space. And in this picture, let me in this picture, let me think about what the closed points of U are. So in the green locus, ideal sheaves become part of these extensions. And an extension, a non-split extension can be degenerated to a split extension. So in this, on the left side, on the green side, everything degenerates to the unique sheaf F. On the red side, the same thing happens because, again, we have a non-split extension and it degenerates to the split extension. So it is something in the closure of this locus in the stack. And so the only locus that is unchanged is the locus where the point is not in P1. So let's see what's happening. So we have P1 in here. And where does this P1 go in X bar? It has to go to the only point that represents the split extension. Because this point, like this blue locus, lies in the closure of the green locus. And so this gives us a 90 degrees rotated picture from the beginning here. So we looked at a variety X. We took a subvariety P1, and we were able to give a contraction. And so this is an interesting consequence that we can contract rational curves using the fancy machinery of stacks. And previously, this has been known. Artin can, by works of Artin, we can contract curves on surfaces with some condition. We cannot contract an arbitrary curve on a surface. It has to be P1 because the ideal sheaves of points on P1 are all isomorphic, so they give us just one point to which P1 contracts. Specifically for contracting rational curves, Reed studied this case for contracting rational curves on threefolds. And this is precisely, oh, and I think there is a typo here. And this is precisely our case. We say that the normal bundle should be non-positive. So these are the only two possibilities for the normal bundle to be non-positive for P1 on a threefold. And so we recover the result of Reed that P1 contracts in these cases. And Jimenez further studied when smooth curves of arbitrary genus G contract using, again, like Artin, he used formal neighborhoods. So there are some verifications of on what the cohomology on the formal neighborhood should be, on the formal completion should be. So we don't need to verify any cohomology conditions. We just see whether the normal bundle is non-positive. And so if it is non-positive and if the curve is rigid, then P1 contracts in X bar. And if we cross the wall further and go to U circle, to the right side, so if we just consider the moduli stack, the good moduli space of the red locus of the stack, then this point gets replaced by the projectivization of H1 of the twisted normal bundle. Okay, and it is now 5 minutes to 12. I may want to briefly say that maybe I don't want to give many more examples. I'll just say in words that similar we can get contractions of the form where Y is a P1 bundle. And I think I may want to stop here. And if anyone asks a question about the decay conjecture, I will probably talk about it for like 30 seconds before concluding the talk. Right, thank you for your attention.
Thank you very much for your talk. Are there any questions? Yes, please go ahead.
Hi, thank you very much for the talk. I'm just curious if you've looked at what happens when you consider FPQC stacks instead of just Artin stacks. Like, can you do all this stuff for quasi-coherent sheaves just instead of coherence?
I don't know the behavior of quasi-coherent stacks well. Do you mean considering moduli of objects in QCO?
Yeah, but in particular using the QCO as an FPQC stack and
Yeah,
doing your descent that way.
I don't think I know what you're talking about. So I know that if we consider the moduli of objects in QCO of X in the Artin-Jang way, then their machinery classifies finitely presented families of objects, and this just recovers the stack of coherent sheaves.
I see. Okay.
But I suspect that you may be talking about something different. If you do, I think you might need to be aware that the existence theorem of Alper, Halpern, Leissner, and Heinloth is proved for quasi-compact stacks. And they have a counterexample for a non-quasi-compact stack, so the theorem fails there.
Okay, thank you.
Are there any other questions? Okay, if not, then thank you very much, Svetlana, again for your talk.
Yes, thank you again for having me. This is not exactly a category theory talk, but I hope you could see it as applied category theory or applied categorical methods.
Yes, and it was nice that you gave the translation out of the term, so it was very helpful. Thank you very much.
All right, and I will probably see some of you in the future.